There's a certain quiet hum beneath the surface of modern technology, something subtle, almost easy to ignore, yet carrying the weight of a potential shift in how reality itself is understood. Tonight, we're going to sit with that idea, not rush it, not dramatize it, but slowly examine it, piece by piece, until what first seemed abstract begins to feel strangely tangible. Because quantum computers are often presented as just the next step in computing. Faster machines, better calculations, bigger possibilities. But if you look a little closer, the story becomes less about speed and more about the nature of reality itself. Before we go deeper, take a moment to settle in. And if you enjoy exploring ideas like this, quietly, thoughtfully, without jumping to conclusions, consider subscribing. And let me know where you're listening from tonight. There's something grounding about realizing how many different places, different perspectives, all converge into the same curiosity. Now, the mainstream explanation of quantum computers is, on the surface, straightforward. Classical computers, the ones we use every day, operate on bits. These bits are simple. They are either a 0 or a 1. Everything your computer does, every image, every message, every video, ultimately reduces down to long strings of these binary states. Predictable, structured, logical. Quantum computers, however, use something different. They use what are called qubits. And unlike classical bits, qubits don't have to be just 0 or 1. They can exist in something known as superposition, meaning they can be both 0 and 1 at the same time, at least until they are measured. That idea alone already begins to stretch intuition, because we're not used to systems that behave this way. In everyday life, things are definite. A coin is either heads or tails. A light is either on or off. But in the quantum world, the coin can be both simultaneously, existing in a kind of unresolved state until observation forces a result. Scientists describe this using precise mathematics, and the models work. Experiments confirm it, but the underlying why remains less settled. And this is where things begin to get interesting. Because if quantum computers rely on superposition to function, then they are not just faster machines. They are machines that operate using a fundamentally different layer of reality. When a quantum computer performs a calculation, it isn't simply trying one possibility after another very quickly. Instead, it is in some sense exploring multiple possibilities at once. This is often described as parallelism, but that word can be misleading. It suggests something mechanical, something structured, but the actual process is far less intuitive. Mainstream physics explains this through the mathematics of quantum mechanics. The system evolves according to probabilities, and when measured, those probabilities collapse into a single outcome. No mystery required, just complex equations doing what they're supposed to do. And for practical purposes, this explanation is enough. Engineers can build systems, run algorithms, and produce results without needing to fully resolve the philosophical implications. But if you pause here, just for a moment, there's an uncomfortable question hiding beneath the surface. If a quantum computer is somehow evaluating multiple possibilities at once, where are those possibilities actually existing? This is where alternative interpretations begin to quietly enter the conversation, not as established facts, but as attempts to make sense of something that resists simple explanation. One of the more well-known interpretations is the idea that these multiple states correspond to multiple realities, sometimes referred to as the many worlds interpretation of quantum mechanics. In this view, every possible outcome doesn't just exist as a probability, it actually happens, but in separate branching versions of reality. Now, it's important to stay grounded here. This interpretation is not universally accepted. Many physicists treat it as one of several possible ways to understand quantum behavior, not as a literal description of reality. But the fact that it even remains on the table is worth noticing. Because if, even hypothetically, a quantum computer is leveraging processes that span multiple possible states, then its computations are not confined in the same way classical computations are. It would mean that the machine is not just processing information, but interacting with a deeper structure of reality, one that we don't fully understand. And there's another layer to this. Quantum systems don't just exhibit superposition. They also exhibit something called entanglement. This is where two or more particles become linked in such a way that the state of one instantly influences the state of another, regardless of distance. Einstein famously referred to this as spooky action at a distance, not because it was mystical, but because it challenged the idea that information must travel through space in a conventional way. In quantum computing, entanglement is not a side effect. It's a resource. It's what allows qubits to work together in ways that amplify computational power. Instead of operating independently, they form a connected system where the state of each qubit depends on the others. This creates an exponential increase in complexity and potential. But again, if you slow down and look at what's actually being described, it raises questions. How does information seem to coordinate itself across space without a clear signal traveling between points? The mainstream answer is that no usable information is transmitted faster than light, and therefore the laws of physics remain intact. And mathematically, this holds true. But conceptually, it still feels incomplete. Because something is clearly happening. Something that doesn't map neatly onto our everyday understanding of cause and effect. And so, when you combine superposition and entanglement, you end up with a system that behaves in ways that seem almost detached from classical reality. A system where outcomes are not determined until they are observed, where components remain connected across distance, where multiple possibilities exist simultaneously, influencing each other in subtle ways. Quantum computers are built directly on top of these principles, which leads to a quiet but persistent thought, one that doesn't demand an answer but invites consideration. If we are able to engineer machines that operate using these deeper quantum rules, does that suggest we are beginning to access a layer of reality that has always been there, just hidden beneath the surface? Or are we simply building tools that exploit mathematical patterns without needing to fully understand what those patterns represent? Because historically, technology often arrives before full understanding. We used electricity long before we understood it at a fundamental level. We harnessed fire long before we knew the chemistry behind combustion. And in each case, the practical application came first. The deeper explanation followed much later. So it wouldn't be unusual if quantum computing is following a similar path. But there's a subtle difference here. Electricity, fire, mechanics, these are all phenomena that fit eventually into a coherent picture of physical reality. They may have been mysterious at first, but they didn't fundamentally challenge the nature of existence itself. Quantum mechanics, on the other hand, still does. Even after decades of research, the interpretation of quantum behavior remains open. The equations work perfectly, but what they mean is still debated. And quantum computers are not just theoretical constructs anymore. They are real machines, being developed, tested, and improved by major research institutions and companies around the world. Which means we are no longer just observing quantum phenomena in controlled experiments. We are building systems that depend on them. And that shift from observation to application is where things often begin to accelerate. Because once a technology becomes useful, investment follows, development speeds up, and questions that were once considered purely philosophical start to have practical implications. For example, quantum computers have the potential to break certain types of encryption, systems that currently secure global communication. That's not speculation, it's a widely acknowledged possibility. Governments and organizations are already preparing for what's called post-quantum cryptography, anticipating a future where current methods are no longer sufficient. But beyond security, there's something else. Quantum computers may allow us to simulate complex systems that are currently beyond reach. Molecules, materials, even biological processes. This could lead to breakthroughs in medicine, energy, and technology. And from a mainstream perspective, this is where the focus remains. Practical benefits, measurable progress. Yet beneath that practical layer, the deeper questions remain quietly unresolved. What exactly is a quantum state before it is observed? What does it mean for something to exist in multiple possibilities at once? And when a quantum computer chooses an outcome, what determines that choice? These are not questions with simple answers. And maybe that's part of what makes this topic so quietly compelling. Because unlike many areas of science, where uncertainty gradually disappears as knowledge increases, quantum mechanics seems to preserve a certain level of mystery, no matter how much we learn. The models improve, the predictions become more accurate, but the underlying nature of reality remains just slightly out of reach. So as we continue this exploration, we're not trying to solve these questions, not tonight. We're simply going to follow them, carefully, examining what we know, where the gaps are, and what those gaps might suggest, without rushing to conclusions. Because sometimes, the most interesting insights don't come from answers. They come from the places where the answers are still missing. If you stay with that thought for a moment, that quiet gap between what we can calculate and what we can truly explain, it begins to reveal something subtle about the way quantum computing is usually presented. Most explanations focus on what these machines will do, breaking encryption, simulating molecules, optimizing complex systems. But far less attention is given to what they might be quietly revealing about the structure of reality itself. Because if a technology consistently works, even while our interpretation of the underlying mechanics remains incomplete, then the technology becomes a kind of probe. Not just a tool for solving problems, but a way of interacting with something deeper than our current models fully capture. To understand why this matters, it helps to look at how quantum computing actually behaves when it is running. In classical systems, you can trace the steps. A calculation begins here, moves there, follows a sequence, and eventually arrives at a result. Even if the process is extremely fast, it is still, at its core, sequential and logical. But in quantum systems, that sense of step-by-step progression becomes difficult to pin down. When qubits are placed into superposition and entangled with each other, the system as a whole evolves in a way that doesn't map cleanly onto a linear chain of events. It's not that the steps don't exist. It's that they don't exist in a form we can easily observe or describe. And this creates a peculiar situation. Because when a quantum computer produces an answer, we can verify that the answer is correct. But the exact path it took to get there is often not directly accessible. The computation happens in a space of possibilities, and when we measure the result, we only see the final outcome, not the full structure of how that outcome emerged. In some cases, trying to observe the process too closely actually disrupts it, collapsing the very superpositions that allow the computation to work in the first place. From a mainstream perspective, this is simply how quantum mechanics operates. Measurement affects the system. Observation collapses probability distributions into definite states. These are well-established principles, tested repeatedly. But if you take a step back, there's an interesting implication hidden in that behavior. It suggests that there are processes occurring which are real enough to produce measurable outcomes, but not directly observable in the way we might expect. And that's not something we encounter often in classical systems. Usually, if something has an effect, we can trace it. We can follow the chain of cause and effect, even if it's complex. But here, the chain exists in a form that resists direct inspection. It's almost as if the computation is happening behind the layer of reality we normally interact with, only becoming visible at the moment of measurement. Now, again, the standard explanation doesn't require anything beyond established physics. The mathematics of quantum mechanics accounts for this behavior precisely. There's no need to assume hidden dimensions or alternate realities. The system evolves according to known equations, and the probabilities collapse when measured, clean, consistent, and sufficient for practical use. But the question that naturally follows is whether that explanation is complete or simply effective. Because throughout the history of science, there have been moments where the equations worked long before the deeper meaning was understood. The equations for gravity described planetary motion accurately for centuries before the underlying nature of space-time was reinterpreted. The equations for thermodynamics worked before the atomic structure of matter was fully accepted. In each case, the math came first, the conceptual understanding followed. So when it comes to quantum computing, it's worth asking whether we are in a similar phase, using a system successfully without yet fully grasping what it implies. And there's another detail that tends to get less attention, but becomes important if you look closely. Quantum computers are extremely sensitive, not just in a general sense, but in a very specific, almost fragile way. The quantum states they rely on can be disrupted by the slightest interaction with the environment: heat, electromagnetic noise, even subtle vibrations. This is why many quantum systems operate at temperatures close to absolute zero. Not because it's convenient, but because it's necessary to maintain coherence, the delicate state where superposition and entanglement can persist long enough to perform meaningful computations. From a technical standpoint, this fragility is a challenge. Engineers are constantly working to isolate quantum systems, to shield them from interference, to extend coherence times. And progress is being made steadily, methodically. But if you think about it from a slightly different angle, that fragility might also be telling us something, because it suggests that the quantum behavior we're relying on isn't the default state of the world we experience day to day. It's something that exists beneath the surface, easily disrupted by interaction with the larger environment. Almost like a deeper layer that becomes visible only under very controlled conditions. And that raises an interesting question. Is the classical world, the stable, predictable reality we move through, emerging from this underlying quantum layer? Or is the quantum layer something separate, only accessible under specific circumstances? The mainstream view leans toward the first option. That classical reality emerges from quantum processes through a mechanism known as decoherence. As quantum systems interact with their environment, their superpositions effectively average out, producing the definite states we observe at larger scales. In this view, there's no boundary between quantum and classical, just a transition from one regime to another. But even here, there are open questions. Decoherence explains how quantum possibilities become classical outcomes, but it doesn't fully explain why a specific outcome occurs in any given instance. It describes the loss of coherence, the spreading of information into the environment, but the exact moment of selection remains somewhat ambiguous. And this ambiguity becomes more noticeable when you consider the role of measurement. In quantum mechanics, measurement is not just passive observation. It actively influences the system. But what qualifies as a measurement? Is it any interaction with the environment? Is it the involvement of a conscious observer? Or is it something else entirely? Most physicists avoid tying measurement to consciousness, favoring interpretations that keep the process entirely physical. And that's a reasonable approach. It keeps the theory grounded and testable. But the question hasn't been completely settled, and different interpretations still coexist. So when a quantum computer runs a calculation and produces a result, what exactly has happened at that moment of measurement? Has the system simply followed a probabilistic evolution and settled into a state? Or has something more subtle occurred? Something tied to how information becomes fixed, how possibilities become realities? Again, there's no need to jump to conclusions here. The goal isn't to replace established science with speculation. It's simply to notice where the boundaries of understanding currently are, because those boundaries are often where the most interesting developments begin. And there's one more aspect worth considering, especially as quantum computing continues to develop. Right now, these machines are still in relatively early stages. They are powerful in specific ways, but not yet broadly practical for all types of computation. Researchers refer to the current era as NISQ, Noisy Intermediate Scale Quantum. The systems are large enough to demonstrate real quantum advantage in certain tasks, but still limited by noise, errors, and stability issues. This means we are in a transitional phase. The technology works, but it's not fully mature. And historically, transitional phases are where the most unexpected discoveries tend to occur, because the focus is not just on application, but on understanding. Problems need to be solved, limitations need to be overcome, and in that process, assumptions are tested, sometimes quietly, sometimes dramatically. So as quantum computers become more stable, more scalable, and more integrated into real-world use, it's reasonable to expect that our understanding of quantum mechanics itself may evolve alongside them. Not necessarily in a way that overturns everything we know, but perhaps in a way that fills in some of those persistent gaps, or possibly reveals new ones. Because if there's one pattern that shows up repeatedly in the history of science, it's this. Each time we think we're approaching a complete picture, a new layer of complexity appears. And quantum computing, in its current form, feels very much like the beginning of one of those layers. Not an ending, not a final answer, but the early signs of something deeper, something that we're only just beginning to interact with, one carefully controlled qubit at a time. There's a subtle shift that begins to happen once you move past the basic explanations of quantum computing. A shift from thinking about what these machines are to wondering how far their behavior can actually go. Because up to this point, the discussion has stayed relatively grounded in known principles, superposition, entanglement, decoherence, concepts that, while unusual, are still part of established physics. But as researchers continue to push the limits of these systems, new questions begin to emerge, not from speculation alone, but from the behavior of the machines themselves. One of the most widely discussed ideas in quantum computing is something called quantum advantage, sometimes referred to as quantum supremacy. This is the point where a quantum computer performs a task that would be practically impossible for a classical computer to replicate within a reasonable time frame. From a mainstream perspective, this has already been demonstrated in very specific, controlled scenarios. For example, certain random sampling problems have been solved by quantum systems in minutes, while classical supercomputers would take far longer to approximate the same result. But here's where it becomes interesting, not because of the achievement itself, but because of how difficult it is to verify. When a classical computer solves a problem, we can usually trace the steps, check intermediate values, and confirm the logic along the way. With quantum systems, especially as they scale, this becomes increasingly difficult. In some cases, The result can be verified statistically, but the exact computational pathway remains opaque. It's not hidden in the sense of being secret. It's hidden because it doesn't exist in a form we can easily observe. And that leads to a quiet but important realization. As quantum computers become more powerful, we may reach a point where they can produce correct answers to problems that we cannot independently verify using classical means. Not because the answers are wrong, but because the process required to check them is just as complex as the original computation. Now, from a practical standpoint, this isn't necessarily a problem. If a system consistently produces results that align with experimental data or observable outcomes, we tend to trust it. This is already how many complex models operate today. But with quantum systems, the gap between computation and verification could become much wider, and that opens up an unusual space, because it introduces the possibility of relying on systems that operate beyond our full ability to audit. Not in terms of secrecy, but in terms of sheer complexity. Mainstream research treats this as a technical challenge, developing new methods of verification, error correction, and cross-checking results. And progress is being made in all of these areas. But if you step back slightly, there's a deeper pattern forming. We are beginning to build machines that not only process information differently, but also challenge our ability to fully understand how that processing occurs. And that's a subtle shift, because traditionally, understanding has followed capability. We build something, and then we work to understand it more deeply. But in this case, capability may begin to outpace understanding in a more fundamental way, not just in scale, but in principle. And this becomes even more apparent when you look at the types of problems quantum computers are expected to solve. One major area is optimization, finding the best solution among an enormous number of possibilities. In classical systems, this often involves approximations, heuristics, or brute force search. But quantum algorithms, such as those based on amplitude amplification, can explore these possibilities in a fundamentally different way. Again, the mainstream explanation is mathematical. The system evolves in such a way that correct answers become more likely to appear when measured. Interference patterns reinforce certain outcomes while cancelling others. It's precise, elegant, and supported by theory. But if you translate that into a more intuitive question, it sounds something like this. How does the system know which possibilities to amplify and which to suppress? The standard answer is that it doesn't know anything. It follows the rules of quantum mechanics, and the structure of the algorithm guides the evolution of probabilities. There's no awareness, no intention, just mathematics unfolding over time. And that's important to keep in mind. But even within that framework, there's an interesting implication. The system is not randomly stumbling into answers. It is being shaped, guided, and influenced by interference patterns that exist within a space of possibilities we cannot directly observe. So while there is no need to assign intention, there is still a kind of directional behavior emerging from the system. And that behavior is not something we can easily visualize, because it's not happening in three-dimensional space or even in time as we usually experience it. It's happening in a mathematical space, often described as a high-dimensional Hilbert space, where each possible state of the system corresponds to a point in that space. Now, this is where the conversation can quietly branch into different interpretations. From a strictly scientific perspective, Hilbert space is just a mathematical construct, a way of representing quantum states and their evolution. There's no need to assume it corresponds to a physical place. It's a tool, and it works. But some interpretations take a more literal view. They suggest that this abstract space might correspond in some way to a deeper layer of reality, not necessarily a separate universe in the science fiction sense, but a foundational structure where all possible states exist simultaneously, and where quantum systems evolve before collapsing into observable outcomes. Again, this is not a settled idea. It's one of several ways people have tried to make sense of quantum behavior. But it remains part of the broader conversation, precisely because the standard interpretations leave certain questions open. And quantum computing, by actively using these principles, brings those questions closer to the surface, because we are no longer just observing quantum effects in isolated experiments. We are designing systems that depend on them, scaling them up, and integrating them into real-world applications, which means that whatever interpretation ultimately proves to be most accurate, it will need to account for the behavior of these machines. And there's another layer to consider, one that tends to be less discussed, but becomes increasingly relevant as quantum systems grow in complexity. Error correction. In classical computing, error correction is relatively straightforward. Bits can be duplicated, checked, and corrected using well-understood methods. But in quantum computing, things are more complicated. You can't simply copy a quantum state due to something called the no-cloning theorem. This means that preserving information requires more elaborate strategies, encoding logical qubits into entangled states of multiple physical qubits, detecting errors indirectly, and correcting them without directly measuring the quantum information itself. From a technical standpoint, this is one of the biggest challenges in the field, but conceptually, it introduces another interesting dynamic. We are creating systems where information is maintained without being directly accessible, where errors are corrected without fully observing the data being protected, where the integrity of a computation depends on maintaining states that cannot be fully inspected without destroying them. And that's not how most systems we're familiar with operate. Usually, to preserve something, you need to access it, monitor it, interact with it. But here, interaction can be disruptive. Observation can collapse the very state you're trying to maintain. So the system has to be carefully balanced, operating in a narrow window where it is stable enough to compute, but isolated enough to preserve its quantum nature. And that balance is delicate. Which leads to a broader question, one that doesn't have a simple answer, but feels increasingly relevant as this technology develops. Are we discovering quantum computation? Or are we learning how to carefully align ourselves with processes that have always existed, but were previously inaccessible? Because if quantum mechanics describes the underlying structure of reality, then in a sense, these computations are not being invented, they are being uncovered. We are finding ways to interact with a system that was already there, operating according to its own rules, long before we had the tools to engage with it. And if that's the case, then quantum computers are not just machines, they are interfaces. Interfaces between the classical world we experience and the quantum layer that underlies it. Now, that idea doesn't require any leap into the unknown. It can be interpreted entirely within the framework of established physics. But it also opens the door to a slightly different way of thinking. Not in terms of replacing current explanations, but in terms of expanding how we relate to them. Because instead of viewing quantum mechanics as something abstract and distant, we begin to see it as something we are actively engaging with, shaping, and depending on. And as that engagement deepens, so does the importance of understanding not just how these systems work, but what they might be quietly revealing, not through dramatic breakthroughs, but through small, consistent patterns, emerging one experiment at a time. As quantum computing continues to move from theory into application, another layer begins to come into focus, one that is less about the physics itself and more about how these systems interact with information. Because at its core, computing has always been about transforming information. taking inputs, applying rules, and producing outputs. But with quantum systems, even the concept of information starts to behave differently. In classical systems, information is stable. A bit is either a 0 or a 1, and unless something goes wrong, it remains that way. You can copy it, store it, move it, and inspect it without fundamentally changing its nature. But in quantum systems, information is tied directly to the state of the system, and that state is not fixed until it is measured. This means that quantum information is not something you can fully separate from the process that generates it. From a mainstream perspective, this is simply how quantum information theory is defined. It extends classical information theory into the quantum domain, accounting for superposition, entanglement, and measurement. Researchers have developed precise frameworks to describe how information behaves under these conditions, and these frameworks are consistent with experimental results. But if you pause and look at it conceptually, it suggests something slightly unusual. It suggests that information, at a fundamental level, may not be as static as we tend to assume. Because in a quantum system, information exists in a kind of fluid state, distributed across possibilities, influenced by entanglement, and only becoming definite when it is observed. It's not just stored in one place or one configuration. It's spread out, in a sense, across a range of potential outcomes. And that leads to an interesting question. When a quantum computer processes information, is it simply manipulating data, or is it interacting with the structure of possibility itself? Now, from a practical standpoint, the answer remains grounded. It's manipulating quantum states according to well-defined rules. There's no need to redefine information as something metaphysical, but the language we use, superposition, interference, collapse, hints at processes that are not entirely captured by classical intuition. And this becomes more apparent when you consider how quantum algorithms are designed. Unlike classical algorithms, which follow a clear sequence of steps, quantum algorithms often rely on preparing a system in a particular state, allowing it to evolve, and then extracting information through measurement. The work of the computation happens during that evolution, in a space that we don't directly observe. It's less like following a recipe, and more like setting up conditions and letting a process unfold. And that distinction matters, because it means that the role of the programmer shifts. Instead of specifying every step explicitly, the programmer defines a framework, a set of constraints and transformations, and then allows the quantum system to explore the space of possibilities within that framework. From a mainstream perspective, this is simply a different computational paradigm, but it also introduces a subtle change in how we think about control. In classical systems, control is precise and direct. In quantum systems, control is more about guidance, shaping probabilities, influencing outcomes, but not dictating them in a deterministic way. And that raises another question. If outcomes are influenced but not strictly determined, what does that say about predictability? Because one of the defining features of classical computing is predictability. Given the same input and the same program, you get the same output every time. But in quantum computing, especially for certain types of algorithms, the outcome is probabilistic. You may need to run the same computation multiple times to build up a statistical picture of the result. Now, this is well understood and accounted for in practice. The probabilities are not random in the everyday sense. They are structured, shaped by the algorithm, and converge toward correct answers over repeated runs. But still, there is an element of uncertainty built into the process, and that's not a flaw, it's a feature. Because that uncertainty is what allows quantum systems to explore multiple possibilities simultaneously. It's what gives them their power. But it also means that the relationship between input and output is not always as straightforward as in classical systems. And this brings us to another layer of the conversation, one that sits quietly in the background but becomes more relevant as quantum technologies develop. The relationship between computation and reality. In classical computing, this relationship is relatively simple. The computer models reality, simulates it, processes data about it. There's a clear separation between the system doing the computation and the world being described. But in quantum computing, that separation becomes less clear, because the system itself operates according to the same quantum rules that govern the physical world. It's not just modeling quantum behavior, it is an instance of quantum behavior. And that creates an unusual situation. We are using one part of reality to compute information about another part of reality using the same underlying principles. Now, again, there's nothing inherently mysterious about this from a scientific standpoint. It's consistent with the idea that the universe is governed by quantum mechanics at a fundamental level. But it does blur the line between simulation and participation. Because when a quantum computer simulates a molecule, for example, it's not just approximating the behavior using classical abstractions, it's using quantum states to represent quantum states. There's a kind of direct mapping between the system and what it's modeling, and that leads to a subtle shift in perspective. Instead of thinking of computation as something separate from the physical world, we begin to see it as something embedded within it. A process that doesn't just describe reality, but operates as part of it. And that idea becomes even more interesting when you consider the scale at which quantum effects are typically observed. For most of human experience, quantum behavior has been confined to the microscopic level. Atoms, particles, small systems. The macroscopic world appears stable, predictable, classical. But quantum computing challenges that boundary. It brings quantum behavior into larger engineered systems, making it something we can interact with more directly. And as these systems scale, the distinction between quantum and classical becomes less about size and more about coherence. If coherence can be maintained, quantum behavior can persist. If it breaks down, classical behavior emerges. That's the general framework. But maintaining coherence at larger scales is difficult. It requires isolation, precision, and careful control. And this difficulty has led some researchers to explore whether there are deeper limits, whether there's a point beyond which quantum behavior cannot be sustained, not just for technical reasons, but for fundamental ones. So far, there's no clear evidence of such a limit. Progress continues, systems improve, coherence times increase, but the question remains open, and it's an important one. Because if there is a fundamental boundary, it would tell us something about the structure of reality itself, where the quantum world ends and the classical world begins, or whether that boundary is simply a matter of complexity, not principle. And as quantum computers continue to develop, they may help answer that question, not directly, but through their behavior, through how far they can scale, how stable they can become, how reliably they can operate. Each of these factors becomes a kind of measurement, not just of engineering progress, but of the underlying rules they depend on. And so, quietly, without much attention outside of specialized circles, quantum computing becomes something more than a technological advancement. It becomes an ongoing experiment, not just in building better machines, but in exploring the limits of what is physically possible. And like many experiments at the edge of understanding, it doesn't provide immediate answers. Instead, it reveals patterns that, over time, begin to form a picture. Not a complete picture, not yet, but enough to suggest that what we are interacting with may be deeper than it first appears. As the picture continues to take shape, there's another dimension of quantum computing that begins to stand out, not in terms of what these systems calculate, but in how they relate to time itself. Because in classical computing, time is straightforward. Operations happen in sequence: step 1, then step 2, then step 3. Even when processes run in parallel, they are still anchored to a timeline that moves forward in a clear, measurable way. But in quantum systems, that sense of orderly progression becomes less rigid. When a quantum computation runs, the system evolves according to equations that are, at their core, reversible. This is a detail that often gets overlooked, but it matters. In classical computing, many operations are irreversible. You lose information as you go. For example, if you take 2 bits and combine them into one output, you can't always reconstruct the original inputs from that output alone. Information is discarded along the way. Quantum operations, on the other hand, are typically designed to be reversible. The system evolves in a way that, in principle, preserves all information until the moment of measurement. This is tied to the underlying mathematics of quantum mechanics, where the evolution of a closed system is described by unitary transformations, processes that don't lose information over time. Now, from a technical standpoint, this is simply how quantum systems are modeled and controlled. But if you pause and reflect on it conceptually, it introduces a different relationship with time. Because if information is preserved throughout the evolution, then the distinction between past and future becomes less about loss and more about transformation. The system moves through a space of possibilities without discarding them, only resolving into a definite outcome when measured. And that raises an interesting question. Before measurement occurs, is the system moving forward in time in the way we usually think about it? Or is it evolving in a more symmetrical way, where the direction of time is not as clearly defined? Mainstream physics does have an answer to this, at least partially. The fundamental equations of quantum mechanics are time symmetric. They don't inherently distinguish between past and future. The asymmetry we experience, often referred to as the arrow of time, is usually associated with thermodynamics, with the increase of entropy in closed systems. But quantum computing operates in a regime where entropy is carefully managed, where systems are isolated and controlled to maintain coherence. In that narrow window, the usual markers of time's direction become less dominant. And while this doesn't mean that time stops or reverses in any literal sense, it does suggest that the processes inside a quantum computation are not bound by the same intuitive flow we experience in everyday life. They exist in a kind of structured evolution, where the outcome is not determined until the end, and the path taken cannot be easily described in terms of a simple timeline. And this becomes even more intriguing when you consider certain quantum algorithms that appear to work backward from the solution. Now, to be clear, they're not literally receiving information from the future. That would go beyond established physics. But the way these algorithms are constructed allows the final measurement to influence how probabilities evolve throughout the computation. The system is set up so that correct answers interfere constructively, while incorrect ones cancel out. From a mathematical perspective, this is completely consistent. But from an intuitive standpoint, it creates the impression that the solution is shaping the process, rather than the process simply leading to the solution. And that's a subtle but important distinction, because it challenges the usual cause and effect narrative we're used to. In classical systems, causes lead to effects in a clear sequence. In quantum systems, the relationship is more distributed. The entire setup, the initial state, the transformations, and the final measurement works together as a whole. It's less like a chain and more like a pattern. And patterns don't always have a single direction. They exist as structures, where different parts influence each other simultaneously. Now, again, there's no need to interpret this as anything beyond standard quantum mechanics. The mathematics handles it cleanly, but it does invite a different way of thinking about how processes unfold, not just in computing, but potentially in other areas where quantum effects play a role. And this brings us to another aspect of quantum computing that quietly connects to this idea of time and structure: quantum interference. At its core, interference is about how different possibilities interact with each other. When a quantum system evolves, the various potential states don't remain isolated. They combine, reinforce, or cancel each other out. This is how quantum algorithms guide the system toward correct answers. But if you think about it more abstractly, interference implies that possibilities are not just passive options waiting to be selected. They are active participants in the computation. They influence each other. They shape the outcome collectively. And that's not how we usually think about possibilities in classical terms. Normally, a possibility is just something that might happen. It doesn't have any effect until it becomes real. But in quantum systems, possibilities have a kind of presence, even before they are observed, and that presence affects the final result. Now, whether you interpret this as a literal feature of reality or simply a useful mathematical framework depends on your perspective. The mainstream view remains cautious, treating these descriptions as models that work, without necessarily committing to a deeper interpretation. But the consistency of the behavior, the way these systems reliably produce results based on interference patterns, suggests that whatever is happening at this level is not arbitrary. It follows rules, structured rules, rules that we can use, even if we don't fully understand what they represent. And as quantum computers become more advanced, these rules are being explored in increasingly complex ways. Researchers are developing new algorithms, new error correction techniques, new architectures, all of which rely on a deeper understanding of how quantum systems evolve over time. And with each step forward, the boundary between what we can calculate and what we can conceptualize shifts slightly, not dramatically, but enough to keep the questions open. Because if you look at the trajectory of this field, it's not just about building faster machines. It's about refining our interaction with a set of principles that challenge our usual assumptions about time, information, and causality. And that refinement is still ongoing. We're still learning how to stabilize qubits, how to scale systems, how to reduce noise. But alongside those technical challenges, there's a quieter process unfolding, a gradual adjustment in how we think about the nature of computation itself, not as a rigid sequence of steps, but as a dynamic interaction within a structured space of possibilities. And that shift, while subtle, has implications that extend beyond technology, because it suggests that the way we process information, both in machines and potentially in other systems, might not be limited to the linear frameworks we're most familiar with. It opens the door to thinking in terms of patterns, probabilities, and interactions that don't fit neatly into a single timeline. And while that doesn't provide immediate answers, it does expand the scope of the questions we can ask. Questions about how systems evolve, how outcomes emerge, and how much of what we consider fixed is actually the result of deeper processes that are still unfolding beneath the surface. As the exploration deepens, another layer begins to emerge, one that shifts the focus slightly away from the machines themselves and toward the environment they exist within. Because up to this point, it's easy to think of quantum computers as isolated systems, carefully controlled, shielded from interference, operating in specialized conditions. And in practice, that's largely true. But no system exists completely in isolation. Even the most controlled quantum setup is still embedded within a broader physical reality. And that interaction, however subtle, plays a role. In classical computing, the environment is usually treated as something external, something to manage, but not something that fundamentally shapes the computation. Heat, electrical noise, hardware imperfections. These are engineering challenges, but they don't redefine how computation works at a basic level. The logic remains intact, even if the implementation needs refinement. In quantum systems, however, the environment is not just a background factor. It is deeply connected to how the system behaves. This is most clearly seen in the concept of decoherence, the process by which quantum systems lose their coherent properties as they interact with their surroundings. When decoherence occurs, superposition fades, entanglement breaks down, and the system begins to behave more like a classical one. From a mainstream perspective, this is a well-understood phenomenon. It explains why quantum effects are so difficult to observe at large scales, and why maintaining coherence is such a central challenge in quantum computing. But if you look at it from a slightly different angle, it suggests that the boundary between quantum and classical is not fixed. It's dynamic. It depends on how a system interacts with its environment. And that leads to an interesting implication. If the behavior of a system can shift between quantum and classical depending on its level of interaction, then what we perceive as stable, classical reality might itself be the result of constant interaction, an ongoing process of decoherence happening at a massive scale. In other words, the classical world may not be the fundamental layer, but rather an emergent one. Now, this idea is not new. It aligns with mainstream interpretations of quantum mechanics, particularly those that emphasize decoherence as the bridge between quantum and classical behavior. But quantum computing brings this concept into a more tangible form. Because instead of just theorizing about the transition, we are actively managing it. We are creating systems where coherence is preserved just long enough to perform computations, before the inevitable interaction with the environment begins to take over. And that management process reveals something subtle. It shows that the distinction between quantum and classical is not absolute. It's conditional. It depends on isolation, on control, on the degree to which a system is allowed to remain undisturbed. And that raises a broader question. If the classical world emerges from quantum processes through interaction, then what defines the scale at which this transition occurs? Why do we experience a stable, classical reality at the human level, while quantum behavior dominates at the microscopic level? The standard answer involves complexity and interaction. Larger systems have more components, more interactions, more opportunities for decoherence to occur. This effectively suppresses quantum behavior, making classical properties dominant. But even here, there are nuances. Experiments have demonstrated quantum effects in increasingly large systems, molecules, superconducting circuits, even small mechanical resonators. Each time the boundary is pushed slightly further, it suggests that the limit is not strictly defined, but rather a matter of how well coherence can be maintained. And that leads to a quiet but persistent thought. If coherence could be preserved at larger and larger scales, how far could quantum behavior extend? Now, from a practical standpoint, there are enormous challenges. Maintaining coherence in large systems becomes exponentially more difficult. Environmental noise increases, control becomes more complex, and stability becomes harder to achieve. But the absence of a clearly defined theoretical limit keeps the question open. And quantum computing, in its current form, is part of that exploration. Each improvement in coherence time, each increase in qubit count, each reduction in error rates, is not just a technical achievement, it's a data point, a small indication of how far quantum behavior can be extended into systems we can directly interact with. And as those data points accumulate, they begin to outline a pattern, not a complete map, but a trajectory, a sense of direction. And within that trajectory, another question begins to take shape, one that connects the physical behavior of quantum systems with the concept of information we touched on earlier. If information in a quantum system is distributed across possibilities, and if those possibilities are influenced by interaction with the environment, then what role does the environment play in shaping the information itself? In classical systems, the environment can introduce noise, errors, distortions, but the underlying information remains conceptually separate. It exists independently of the environment, even if it's affected by it. In quantum systems, the relationship is more intertwined. When a quantum system interacts with its environment, information doesn't just get corrupted, it gets redistributed. The environment effectively becomes entangled with the system, carrying away pieces of information in a way that contributes to decoherence. This is sometimes described in terms of quantum Darwinism, where certain states become stable because they are redundantly encoded in the environment, making them more likely to be observed. From a mainstream perspective, this is a way of explaining how classical reality emerges from quantum possibilities. The environment acts as a kind of filter, reinforcing certain outcomes while suppressing others. But if you step back and look at the broader picture, it suggests that information is not just processed within a system, it is shaped by the system's relationship with its surroundings. And that's a subtle but important shift, because it means that computation at the quantum level is not entirely self-contained. It is influenced by context, by interaction, by the broader environment in which it occurs. Now, this doesn't mean that quantum computers are somehow aware of their surroundings in any meaningful sense. The processes are still governed by physical laws, not intention or perception. But it does highlight the extent to which these systems are embedded within a larger framework. They are not isolated islands of computation. They are part of a continuous physical process. And that realization becomes more relevant as quantum technologies move closer to real-world integration. Because as these systems scale, they will need to operate in less controlled environments. They will need to interact with classical systems, with networks, with external inputs and outputs. And managing that interaction, preserving coherence while allowing useful communication, becomes one of the central challenges. It's not just about building better qubits, it's about navigating the boundary between quantum and classical in a way that allows both to coexist. And that boundary, as we've seen, is not fixed. It shifts, it adapts, it depends on conditions, which means that as we learn to control it more precisely, we are not just improving technology, we are refining our ability to operate at the edge of two different regimes of reality. And that edge is where many of the most interesting questions tend to appear. Not because it provides clear answers, but because it reveals the limits of our current understanding. Limits that are not static, but moving, evolving alongside the systems we build. And as those systems become more sophisticated, more stable, more integrated, the interaction between quantum processes and the broader environment will only become more important, not just as a technical challenge, but as a window into how information, reality, and interaction are connected at a fundamental level. A window that for now remains only partially open, but wide enough to keep the questions coming. As we continue moving deeper into this quiet landscape of ideas, another thread begins to reveal itself. One that connects quantum computing not just to physics or information, but to something even more subtle, the limits of knowledge itself. Because up to now, we've been looking at what quantum computers do, how they behave, and what they might imply about reality. But there's a quieter question sitting underneath all of that. A question about how much of this process can ever be fully known. In classical systems, there's an underlying assumption that, given enough time and effort, any computation can be understood. You can trace the logic, examine the steps, and reconstruct the path from input to output. Even if the system is extremely complex, the principle remains intact. The process is, in theory, transparent. Quantum systems begin to challenge that assumption in a very specific way. Not because they are intentionally hidden, but because the act of fully observing them changes their behavior. This is something we've touched on before, but it becomes more significant when you think about it in terms of knowledge. If observing a system alters the system, then there may be limits to how completely that system can be known without disrupting it. From a mainstream perspective, this is captured in principles like the uncertainty principle and the measurement problem. These are not new ideas. They've been part of quantum mechanics for decades, tested and refined through countless experiments. But when you bring them into the context of quantum computing, they take on a more practical dimension. Because now, we are not just observing quantum systems, we are relying on them to perform computations. And that reliance introduces a kind of trade-off. To preserve the quantum behavior that makes these systems powerful, we have to limit how much we interact with them. But limiting interaction also limits observation, and limiting observation limits knowledge. So we find ourselves in an unusual position. We can build systems that produce correct results, but we cannot fully observe the process that generates those results without interfering with it. And that raises a subtle but important question. Is there a point at which understanding becomes fundamentally constrained, not by lack of effort or technology, but by the nature of the system itself? Now, the mainstream view doesn't frame it in quite those terms. Instead, it focuses on what can be measured, what can be predicted, and what can be verified. If a system produces reliable results, and those results align with theory and experiment, then the system is considered understood within that framework. But there's still a distinction between predictive understanding and complete transparency. And quantum systems seem to sit somewhere in between. We can predict their behavior statistically. We can design algorithms that guide them toward correct outcomes. But the full detailed picture of what happens during the computation remains partially out of reach. And that's not necessarily a flaw. It may simply be a characteristic of systems that operate at this level. But it does shift the way we think about knowledge. Because instead of expecting complete visibility, we begin to work with partial information, guided by models, probabilities, and patterns. And this approach is already familiar in other areas of science. Weather prediction, for example, relies on complex models that are not fully transparent at every level, yet still produce useful forecasts. Biological systems are understood in terms of interactions and probabilities, rather than precise, deterministic pathways. So in that sense, quantum computing may not be introducing something entirely new, but rather extending a pattern that already exists. The difference is that the limitations here are not just practical, they are built into the structure of the system. And that brings us to another aspect of quantum computing that quietly connects to this idea, the role of randomness. In classical computing, randomness is usually simulated. It's generated through algorithms that produce sequences of numbers that appear random but are ultimately deterministic. True randomness, in a strict sense, is not required for most classical processes. In quantum systems, however, randomness appears to be fundamental. When a quantum state is measured, the outcome is not determined in advance in the classical sense. It is described by probabilities, and the specific result emerges at the moment of measurement. From a mainstream perspective, this is one of the defining features of quantum mechanics. The probabilities are well defined, the statistics are predictable, but individual outcomes are inherently uncertain. And this raises an interesting question. If randomness is built into the system at a fundamental level, what does that mean for computation? Because computation is usually associated with logic, structure, predictability. But here, randomness is not just noise, it's part of the process. Quantum algorithms are designed to work with this randomness, to harness it, to shape it through interference and probability amplitudes. The randomness is not eliminated, it is guided. And that creates a different kind of computational landscape. One where outcomes are not fixed in advance, but emerge from a structured interaction of possibilities. Now again, there's no need to interpret this as anything beyond established physics, but it does invite a different perspective on what computation can be. Not just a deterministic sequence of steps, but a process that incorporates uncertainty as a core component. And this perspective becomes even more relevant when you consider the long-term trajectory of quantum computing. As these systems become more advanced, more stable, more capable, they may begin to tackle problems that are not just computationally difficult, but conceptually complex. Problems where the solution is not a single answer, but a distribution of possibilities. Problems where uncertainty is not something to be eliminated, but something to be understood. And in that context, quantum computing becomes more than a tool for faster calculation. It becomes a way of engaging with complexity, in a way that aligns more closely with how certain aspects of reality actually behave. Not everything is deterministic. Not everything follows a single predictable path. And quantum systems, by their nature, reflect that. Which brings us back to the question of knowledge. If the systems we are building operate in ways that resist full observation, incorporate fundamental randomness, and depend on interactions that cannot be completely isolated, then our understanding of those systems may always involve a degree of approximation, not because we're missing something, but because the system itself does not lend itself to complete transparency. And that idea, while subtle, has broader implications, because it suggests that there may be limits to what can be fully known, not just in quantum computing, but in any system that shares similar characteristics. Limits that are not barriers, but boundaries. Boundaries that define the scope of our models, our predictions, our understanding. And within those boundaries, there is still a vast space to explore. A space where patterns can be identified, relationships can be mapped, and insights can emerge, even if the full picture remains just slightly out of reach. And perhaps that's part of what makes this field so quietly compelling. Not because it provides definitive answers, but because it continuously reveals new layers of questions, each one grounded in real, observable behavior, yet pointing towards something deeper, something that invites careful examination rather than quick conclusions. And as quantum computing continues to evolve, those questions are likely to become more refined, more focused, more connected to the systems we build and the results they produce. Not in a way that resolves the mystery completely, but in a way that makes the mystery more precise, more structured, more accessible, without ever becoming fully transparent. As we move further into this exploration, another layer begins to form. One that shifts the focus slightly outward toward the broader systems that quantum computing may eventually connect with. Because up to now, most of what we've discussed has taken place within controlled environments, laboratories, specialized hardware, carefully isolated conditions. But these systems are not being developed in isolation forever. The long-term goal is integration into networks, into infrastructure, into the larger digital world that already surrounds us. And that transition from isolated systems to interconnected ones introduces a new set of questions. In classical computing, networks are well understood. Information moves from one point to another, encoded in signals, transmitted through physical media, processed and stored along the way. The rules are clear, the pathways are defined, and while complexity can grow, the underlying structure remains consistent. Quantum systems, however, introduce something different, because in addition to transmitting information in the classical sense, they also have the potential to transmit quantum states. This is where the concept of quantum communication comes in, using entanglement and quantum properties to enable new forms of information transfer. From a mainstream perspective, one of the most well-developed applications here is quantum key distribution. This allows two parties to share encryption keys in a way that is theoretically secure, because any attempt to intercept the key would disturb the quantum system and reveal the presence of an eavesdropper. This is not speculative. It has already been demonstrated in real-world experiments, including satellite-based systems. The principles are grounded, the results are measurable, and the technology is gradually advancing. But beyond these practical applications, there's a broader implication worth considering. If quantum systems can be linked across distance through entanglement, then the structure of a network begins to look different. Because in classical networks, connections are defined by physical pathways, cables, signals, transmission times. In quantum networks, entanglement introduces correlations that are not dependent on those pathways in the same way. Now, it's important to stay precise here. Entanglement does not allow for faster-than-light communication in the conventional sense. This is well established. Any usable information still requires classical communication channels. The laws of relativity remain intact, but even within those constraints, the nature of the connection is different. Because entangled systems are not just linked through signals, they share a joint state. A change in one is reflected in the other, not through a transmission of information in the usual sense, but through a correlation that exists as part of the system itself. And when you begin to imagine networks built on top of that principle, the architecture becomes less about sending messages from point A to point B, and more about managing relationships between distributed states. It's a subtle shift, but it matters, because it suggests that information in a quantum network is not just something that moves, it's something that exists across the network as a whole. Now, from a practical standpoint, building such networks is extremely challenging. Maintaining entanglement over long distances requires advanced techniques, quantum repeaters, error correction, precise synchronization. And while progress is being made, we are still in the early stages. But the direction is clear. Researchers are working toward what is sometimes called a quantum internet, a network that combines classical and quantum communication, enabling new forms of computation, security, and coordination. And this is where the conversation begins to expand beyond individual systems. Because once quantum computers are connected, their capabilities may not simply add together, they may interact in ways that are not fully predictable using classical intuition. Distributed quantum computing, for example, involves multiple quantum systems working together, sharing entangled states, performing coordinated operations. The potential here is significant, but so is the complexity. And with that complexity comes a new layer of questions, not just about how these systems will function, but about how their behavior will scale, because scaling in classical systems is often linear or exponential in ways we can model. But scaling in quantum systems may involve interactions that are more difficult to anticipate due to the role of entanglement and interference across multiple components. And that brings us back to a theme that has been quietly present throughout this exploration. The idea that quantum systems are not just larger versions of classical systems, they are fundamentally different in how they process, store, and relate information. And when those differences are extended into networks, the implications become more pronounced. Now again, the mainstream approach remains grounded. Engineers and physicists are focused on building reliable systems, improving stability, developing protocols. The goal is practical functionality, not philosophical speculation. But as these systems grow, the line between practical and conceptual begins to blur, because each new capability reveals something about how these principles behave at scale. And one area where this becomes particularly interesting is synchronization. In classical networks, synchronization is about timing, ensuring that signals arrive when expected, that processes remain coordinated. In quantum systems, synchronization takes on an additional dimension, because maintaining entanglement and coherence across distributed systems requires not just timing, but alignment at the level of quantum states. And that's not something we have much experience with. It requires a level of precision that goes beyond traditional engineering challenges. And it raises questions about how stable such systems can become and how they will behave under real-world conditions. But perhaps the most subtle shift comes when you consider what these networks are actually doing. They are not just transmitting data. They are extending the reach of quantum states. They are creating systems where information is not confined to a single location, but exists across multiple nodes, connected through relationships that are not purely classical. And that begins to change how we think about the boundaries of a system. In classical terms, a computer is a defined object, hardware in a specific place, processing information locally. In a quantum network, the system may be distributed, with its state shared across multiple locations. And that distribution is not just physical, it's informational. The state of the system is defined by the relationships between its parts, not just the parts themselves. Now, whether this leads to entirely new forms of computation or simply more efficient versions of existing ones remains to be seen. But the direction suggests that the future of quantum computing is not just about individual machines becoming more powerful. It's about systems becoming more connected, more integrated, more interdependent. And as that happens, the questions we've been exploring about information, reality, observation, and interaction will likely become even more relevant, not because they need immediate answers, but because they provide a framework for understanding what these systems might be revealing, step by step, connection by connection, as the network begins to take shape. As the network begins to take shape in theory, there's another dimension quietly unfolding alongside it, one that doesn't immediately show up in technical diagrams or engineering roadmaps, but becomes increasingly difficult to ignore the deeper you look. It's the question of scale, not just in terms of size or power, but in terms of how quantum systems might begin to intersect with processes we don't typically associate with computation at all. Because up to this point, quantum computing has been framed largely as a technological evolution. Faster processing, better simulations, more secure communication, all valid, all grounded. But when you step back and look at the underlying principles, superposition, entanglement, probabilistic outcomes, it becomes clear that these are not just computational tools. They are descriptions of how reality behaves at its most fundamental level. And that leads to a subtle but persistent thought. If quantum mechanics governs the behavior of particles, and if those particles make up everything else, then quantum processes are not limited to specialized machines. They are everywhere. Now, in most cases, these processes average out. Decoherence ensures that at larger scales, the quantum behavior becomes effectively classical. That's the standard explanation, and it aligns with observation. We don't see objects existing in multiple states at once. We don't experience entanglement in everyday interactions. The world appears stable, consistent, predictable, but the underlying layer remains. And quantum computing, in a sense, is a way of isolating and amplifying that layer, bringing it into a form we can interact with directly. Which raises an interesting question. Are there other systems, natural systems, that already operate in ways that resemble quantum computation? Now, this is an area where mainstream research is cautious but not dismissive. There are studies exploring quantum effects in biological systems, photosynthesis, for example, where energy transfer appears to involve quantum coherence under certain conditions. There's also research into the behavior of certain enzymes, and even into the possibility of quantum effects playing a role in processes like navigation in birds. None of this suggests that biological systems are quantum computers in the way we build them. That would be an oversimplification. But it does indicate that quantum principles may play a role in systems that are not artificially isolated or engineered to the same degree. And that opens up a line of thought that is worth examining carefully. If quantum effects can persist, even briefly, in complex, noisy environments, then the boundary between quantum and classical may be more flexible than we assume. Not in a way that overturns established physics, but in a way that suggests there may be pockets of quantum behavior embedded within larger systems. And if that's the case, then quantum computing is not just about creating something new. It's about learning how to recognize and harness patterns that may already exist in nature. Now, this doesn't mean that everything is secretly running quantum algorithms behind the scenes. That would be a leap beyond the evidence. But it does suggest that the principles we're working with are not confined to laboratories. They are part of the fabric of the world. And as we become more skilled at working with them, we may begin to notice connections that were previously invisible, connections between different fields, different systems, different scales. Because one of the recurring patterns in science is that discoveries in one domain often reveal parallels in others. Electricity, once understood, showed up in biological systems, in chemistry, in technology. Information theory, once developed, found applications in communication, computing, and even genetics. So it's reasonable to ask whether quantum information, the way information behaves at the quantum level, might also have broader relevance, not necessarily in a direct, one-to-one way, but in terms of underlying patterns. And this brings us to another subtle point. Quantum computing forces us to think about information in a more abstract way, not just as bits or data, but as something that can exist in multiple states, interact across distance, and evolve in ways that are not strictly linear. And that perspective can influence how we approach problems beyond computing, because it encourages a different kind of thinking, less focused on fixed states, and more focused on relationships, probabilities, and interactions. Now, again, it's important to stay grounded. This doesn't mean that quantum mechanics can be directly applied to every complex system. Different domains have their own rules, their own constraints, but the shift in perspective is still meaningful because it expands the range of models we can consider. And sometimes that's where progress begins. Not by replacing existing frameworks, but by adding new ones. And as quantum computing continues to develop, it may contribute to that expansion in ways that are not immediately obvious, not just through its direct applications, but through the ideas it introduces, the questions it raises, the patterns it reveals. And there's another aspect of scale that becomes relevant here as well. Not just how small quantum systems are, but how large their implications might be. Because even a relatively small quantum computer, if it reaches a certain level of capability, can have an outsized impact. Breaking encryption, for example, doesn't require a system that models the entire universe. It requires a system that can perform specific tasks more efficiently than classical counterparts. And once that threshold is crossed, the effects ripple outward. Security systems change, communication protocols adapt, entire industries adjust. So the influence of quantum computing is not just a function of its size or complexity, but of where it intersects with existing systems. And that intersection is likely to expand over time, gradually at first, then more noticeably, as capabilities increase and applications become more practical. And within that expansion, the deeper questions remain, not as obstacles, but as a kind of background layer. A reminder that while we are building tools and solving problems, we are also interacting with principles that are not yet fully understood. Principles that operate at the foundation of reality and that continue to reveal new details as we explore them. And perhaps that's one of the most interesting aspects of this entire field. Not just what it can do, but what it quietly suggests. About how information behaves, about how systems evolve, about how much of what we consider stable and fixed might actually be the result of deeper processes unfolding beneath the surface. Processes that we are only beginning to engage with in a controlled, deliberate way, one qubit at a time. As the ideas continue to unfold, there's another direction worth following, one that shifts attention away from the machines, the networks, and even the physical systems, and instead focuses on something more abstract, but no less important. The concept of limits. Not just technical limits, but fundamental ones. Because every field, no matter how advanced, eventually runs into boundaries. And quantum computing, for all its potential, is no exception. Up to this point, much of the discussion around quantum computers has centered on what they might achieve, solving problems that are currently intractable, simulating systems beyond classical reach, reshaping encryption and communication. These possibilities are real, and they are grounded in well-established theory. But alongside that optimism, there's a quieter conversation happening within the field. A conversation about what quantum computers cannot do. From a mainstream perspective, this is framed in terms of computational complexity. There are classes of problems that quantum computers are expected to solve more efficiently than classical ones, but there are also problems that remain difficult, regardless of the computational model. Quantum computing does not magically make all hard problems easy. It shifts the landscape, but it doesn't eliminate complexity. And that distinction matters, because it reminds us that even as we explore new computational paradigms, the concept of limitation doesn't disappear, it evolves. For example, algorithms like Shor's algorithm demonstrate that quantum computers can factor large numbers efficiently, which has major implications for encryption. But for many other problems, the speed-up is more modest, or in some cases, not yet clearly established. And this leads to an important realization. Quantum computing is not a universal shortcut. It is a specialized tool, one that excels in certain areas, but not in all. Now, that might seem like a straightforward point, but it becomes more interesting when you consider why those limits exist, because they are not just practical constraints. They are tied to the underlying structure of computation itself. And that brings us to a deeper question. Are there problems that are fundamentally beyond computation, regardless of the system used? This is where the conversation intersects with ideas from theoretical computer science. Concepts like undecidability, problems that cannot be solved by any algorithm, classical or quantum. The most well-known example is the halting problem, which shows that there is no general method to determine whether an arbitrary program will eventually stop or run forever. Quantum computing does not change this. It operates within the same fundamental boundaries. And that's a subtle but important point, because it suggests that even as we expand our computational capabilities, there are limits that remain fixed. Not because of technology, but because of the structure of logic and mathematics. Now, from a practical standpoint, these limits may not affect everyday applications. Most real-world problems fall into categories where computation is possible, even if it's difficult. But as systems become more advanced, and as we begin to rely on them for increasingly complex tasks, these boundaries may become more relevant. not as obstacles, but as guideposts, indicators of where certain approaches may reach their limits. And this idea of limits connects to another aspect of quantum computing that is often discussed in more technical terms, but has broader implications. Resource constraints. Quantum systems require specific conditions: low temperatures, precise control, isolation from noise. Scaling these systems is not just a matter of adding more components. It involves managing an increasingly complex set of variables. From a mainstream perspective, these are engineering challenges. Difficult, but not necessarily insurmountable. Progress is steady, and new techniques are being developed to address these issues. But even here, there's an open question. Are these challenges purely technical, or do they hint at deeper constraints? In other words, is there a point at which maintaining large-scale quantum coherence becomes not just difficult, but fundamentally limited? So far, there's no definitive answer. Some researchers believe that with enough innovation, large-scale, fault-tolerant quantum computers will become a reality. Others are more cautious, suggesting that unforeseen limitations may emerge as systems grow more complex. And history offers examples of both outcomes. Some technologies scale smoothly once key challenges are solved. Others encounter barriers that require entirely new approaches. So once again, we find ourselves in a familiar position, working at the edge of what is known, without a clear view of where the boundary ultimately lies. And this uncertainty is not a weakness, it's a natural part of exploration, because limits, when understood clearly, often lead to new directions, new ways of thinking, new frameworks that extend beyond the original problem. And this brings us to a more abstract but equally important consideration: the relationship between computation and understanding. Because even if a quantum computer can solve a problem, does that mean we understand the solution? In classical systems, there is often a closer connection between computation and comprehension. The steps of an algorithm can be examined, the logic can be followed, the reasoning can be reconstructed. In quantum systems, as we've discussed, that connection can become less direct. The system produces an answer, but the path it takes may not be fully accessible. And that raises an interesting question. If we rely on systems that operate beyond our intuitive understanding, how does that affect our relationship with knowledge? Now, this is not a new issue. It appears in other areas of science and technology as well. Complex models, machine learning systems, simulations, all can produce results that are difficult to interpret in detail. But quantum computing introduces this dynamic at a more fundamental level, because the opacity is not just due to complexity, it is tied to the nature of the system itself. And that may require a shift in how we think about understanding, from a focus on detailed mechanisms to a focus on reliable patterns and outcomes, from complete transparency to structured trust. Now, that doesn't mean abandoning the goal of deeper insight. Research continues, interpretations evolve, new techniques are developed to probe quantum systems more effectively. But it does suggest that the relationship between computation and explanation may not always be straightforward. And that idea, while subtle, has broader implications, because it touches on how we interact with increasingly complex systems, not just in quantum computing, but in other areas as well. How we verify results, how we build confidence, how we decide what counts as understanding. And as quantum computing continues to develop, these questions are likely to become more prominent, not because they need immediate answers, but because they shape how the technology is integrated into the world, how it is used, how it is trusted, and how it is interpreted. So while much of the focus remains on what quantum computers can achieve, there is value in also considering their limits, not as constraints to be overcome, but as part of the landscape. A landscape that defines what is possible, what is practical, and what remains just beyond reach. And within that landscape, the exploration continues, carefully, deliberately, one question at a time. As the exploration continues, there's another layer that begins to come into focus, one that is less about capability or limitation and more about interpretation. Because throughout the development of quantum computing and quantum mechanics more broadly, there has always been a quiet divide between what the mathematics tells us and what we believe it means. Up to now, we've stayed mostly within the practical and observable. What these systems do, how they behave, where the challenges lie. But beneath all of that, there is an ongoing effort to answer a more fundamental question. What is actually happening when a quantum system evolves? From a mainstream perspective, there is no single agreed-upon answer. The equations of quantum mechanics are clear, precise, and extraordinarily successful at predicting outcomes. But the interpretation of those equations, the underlying picture of reality they represent, remains open. And this is where things begin to branch. One widely accepted approach is often referred to as the Copenhagen interpretation. In this view, the quantum state represents a set of probabilities, and the act of measurement causes those probabilities to collapse into a definite outcome. It's a practical framework, one that aligns well with experimental results, and it avoids making claims about what exists beyond what can be observed. But even within this interpretation, there is a subtle gap, because it describes how probabilities become outcomes, without fully explaining why a particular outcome is selected in any given instance. And for many purposes, that gap is acceptable. The theory works. The predictions match reality. The system behaves as expected. But as we've seen, quantum computing begins to push against that boundary. Because we are no longer just observing quantum systems. We are using them, engineering them, relying on them to perform specific tasks. And that practical engagement tends to bring interpretive questions closer to the surface. Not because they are required for the technology to function, but because they become harder to ignore. And this is where alternative interpretations start to gain attention, not as replacements for established physics, but as different ways of framing the same underlying mathematics. We briefly mentioned the many worlds interpretation earlier. In that view, all possible outcomes of a quantum event actually occur, each in its own branch of reality. There is no collapse, only a continuous branching of states. Now, it's important to emphasize that this is an interpretation, not a confirmed fact. It makes the same predictions as other interpretations in most cases, and it remains one of several competing frameworks. But it does offer a different perspective on what quantum computation might represent. Instead of probabilities collapsing into a single outcome, the computation could be seen as evolving across a vast landscape of possibilities, with the final measurement selecting one branch from that structure. Again, this is not something we can directly observe. It's a way of thinking about the process, not a definitive description of reality. But it raises an interesting question. If a quantum computer explores multiple possibilities simultaneously, is that exploration purely mathematical, or does it correspond to something physically real? The mainstream answer remains cautious. The mathematics works regardless of interpretation, so there is no need to commit to one view over another. But the question persists, quietly. And it becomes more intriguing when you consider how consistent the results are. Quantum systems behave in ways that align precisely with the equations, the interference patterns, the probability distributions, the outcomes, all match the predictions. So whatever interpretation we choose, it must account for that consistency. And this leads to another perspective that has gained attention in recent years: the idea that the quantum state does not represent reality directly, but rather our knowledge of it. In this view, often associated with interpretations like cubism, the wave function is a tool for predicting outcomes based on available information, not a physical entity that exists independently. From this standpoint, quantum mechanics is less about describing an objective reality and more about modeling our interaction with it. Now, this approach has its own implications, because it shifts the focus from what is happening to what can be known about what is happening. And that connects back to something we discussed earlier: the limits of observation, the role of measurement, the idea that certain aspects of quantum systems may not be fully accessible. So instead of asking what the system is doing in an absolute sense, the question becomes how our knowledge of the system evolves as we interact with it. And once again, quantum computing sits right at the center of this conversation. Because it depends on these principles. It operates within this uncertainty. It produces results that are consistent, reliable, and useful, even as the interpretation of those results remains open. And that creates an unusual situation. We are building technology based on a theory that works perfectly in practice, while still debating what it means at a deeper level. Now, this is not entirely unprecedented. There have been other moments in science where practical success preceded conceptual clarity, but the scale and precision of quantum mechanics make this case particularly striking, because the theory is not just approximately correct, it is extraordinarily accurate, and yet the underlying picture of reality remains unsettled. And this brings us to a more reflective question. Does interpretation matter if the predictions are correct? From a purely practical standpoint, the answer might be no. Engineers can build quantum computers, researchers can develop algorithms, applications can be realized, all without resolving the interpretive debates. But from a broader perspective, interpretation shapes how we think. It influences the questions we ask, the directions we explore, the assumptions we make. And in a field as foundational as quantum mechanics, those assumptions can have far-reaching effects, because they determine how we conceptualize reality itself, not just as a collection of observable phenomena, but as a structured system with underlying rules. And quantum computing, by bringing these rules into a tangible form, makes those conceptual questions more immediate, more relevant, more connected to what we are actually doing. So as we continue this exploration, it's worth keeping in mind that there may not be a single, final interpretation waiting to be discovered. There may instead be multiple frameworks, each capturing a different aspect of the same underlying reality. And quantum computing, in its own quiet way, may help us navigate between them, not by providing definitive answers, but by revealing patterns that any interpretation must account for, patterns that emerge from real systems, real experiments, real computations, patterns that don't depend on how we choose to describe them, but that still invite us to try, carefully, thoughtfully, without rushing to conclusions. Because sometimes the act of interpretation is not about finding the one correct answer. It's about refining the way we ask the question. As we move further into this quiet investigation, another layer begins to take shape. One that feels less technical at first glance, but becomes increasingly relevant the more you sit with it. It's the relationship between quantum computing and prediction. Not just predicting outcomes in a narrow computational sense, but the broader idea of anticipating complex systems, understanding patterns before they fully unfold. Because at its core, much of computation, classical or quantum, is about prediction. You input data, apply a model, and generate an output that tells you something about what will happen. or what is most likely to happen. Weather forecasts, financial models, molecular simulations, all of these rely on the ability to process information and project it forward. Quantum computing enters this space with a very specific promise. Not that it will predict everything, but that it may allow us to model systems that are currently too complex to simulate accurately with classical methods. And from a mainstream perspective, this is one of its most compelling applications. Chemical reactions, for example, involve interactions between many particles, each governed by quantum mechanics. Simulating these interactions classically becomes exponentially difficult as the system grows. Quantum computers, in principle, can represent these systems more naturally because they operate under the same underlying rules. So the idea is straightforward. Use a quantum system to simulate another quantum system, and in doing so, gain insights that would otherwise be inaccessible. But if you slow down and examine that idea more carefully, it begins to open up a deeper question. When a quantum computer simulates a system, is it predicting the system, or is it, in some sense, recreating its behavior? Now, the mainstream answer is that it's a simulation, a model. It produces outputs that correspond to the behavior of the system being studied within certain limits of accuracy. There's no need to assume anything more than that, but the distinction between simulation and replication becomes less clear when both systems are governed by the same fundamental rules. Because if the model and the system share the same underlying structure, then the simulation is not just an approximation in the classical sense, it's a direct mapping of one quantum process onto another. And that's a subtle shift, because it suggests that prediction, in this context, is not just about extrapolating from data, but about aligning one system with another in a way that allows their behaviors to correspond. Now, this doesn't mean that the simulation becomes identical to the system being modeled. There are still limitations, approximations, practical constraints, but the relationship is closer than in classical simulations. And that closeness raises an interesting thought. If we can simulate increasingly complex systems with high fidelity, where does the boundary lie between understanding a system and effectively reproducing it? Again, this is not a question with a simple answer. It depends on definitions, on context, on what we mean by understanding. But it does highlight how quantum computing may change the way we approach certain problems. Instead of relying solely on abstract models, we may begin to rely more on direct simulation, on creating systems that behave like the systems we're studying, and observing the results. And this approach has both strengths and limitations. On one hand, it allows for a level of detail and accuracy that may not be achievable through classical methods. On the other hand, it can make interpretation more challenging. If the system produces an outcome, but the internal process is not fully transparent, then understanding becomes less about tracing every step, and more about analyzing patterns and results. And this connects back to something we touched on earlier, the relationship between computation and explanation. Quantum computing may allow us to generate answers to complex questions, but those answers may not always come with a clear, intuitive explanation. They may need to be interpreted, tested, validated through other means. And that's not necessarily a limitation. It's a different way of engaging with knowledge, one that emphasizes results and patterns, rather than step-by-step reasoning. Now, there's another dimension to prediction that becomes relevant here as well. Not just predicting physical systems, but predicting behavior in more abstract domains. Optimization problems, for example, often involve finding the best solution among a vast number of possibilities. These problems appear in logistics, finance, machine learning, and many other areas. Quantum algorithms may offer advantages in exploring these possibility spaces more efficiently. But once again, The process is not straightforward. The system evolves, probabilities shift, interference patterns guide the outcome, and the final result emerges through measurement. And while this can produce useful solutions, it also raises a question. How much of the prediction is embedded in the structure of the algorithm, and how much is emerging from the dynamics of the quantum system itself? In classical computing, the algorithm is explicit. It defines the steps, the logic, the pathway to the solution. In quantum computing, the algorithm defines a framework, but the system's evolution plays a more active role in shaping the outcome. So prediction becomes a collaboration between design and dynamics, between what we set up and how the system behaves within that setup. And that collaboration introduces a level of subtlety, because it means that understanding the outcome requires understanding both the algorithm and the system's response to it. And as systems become more complex, that interaction becomes more intricate, more layered, more difficult to fully unpack, but also potentially more powerful, because it allows for the exploration of solution spaces that would otherwise remain out of reach. And this brings us back to the broader theme that has been quietly present throughout this exploration. The idea that quantum computing is not just extending classical methods, but introducing a different way of interacting with complexity, not by eliminating uncertainty, but by working with it, not by simplifying systems, but by engaging with their full structure. And in doing so, it may change how we think about prediction itself, from a process of narrowing down possibilities to a process of navigating them, from a search for a single answer to an exploration of structured outcomes. Now, this doesn't replace classical approaches. In many cases, classical methods will remain more practical, more efficient, more accessible. But in certain domains, particularly those that are inherently quantum or highly complex, this new approach may offer something different. Not just faster results, but a different relationship with the problem itself. And as quantum computing continues to develop, that relationship will likely become more refined, more integrated into how we approach certain types of questions, not as a universal solution, but as a specialized perspective, one that complements existing methods, while also expanding the range of what we can explore. And within that expansion, the deeper questions remain, not as obstacles, but as part of the process, guiding it, shaping it, keeping it open. Because in a field like this, where the boundaries are still being defined, the questions are not something to be resolved quickly. They are something to be followed, carefully, patiently, as the patterns continue to emerge. As we continue to follow these threads, there's another perspective that begins to emerge. One that shifts the focus from prediction and simulation towards something quieter, but perhaps more foundational. The idea of representation. Because at every level of computing, classical or quantum, we are dealing with representations of reality. Data stands in for objects, symbols stand in for processes, mathematical structures stand in for physical systems. But quantum computing introduces a form of representation that behaves differently from anything we're used to. In classical systems, representation is straightforward. A bit represents a value. A string of bits represents more complex information. The relationship between the representation and what it represents is defined, stable, and most importantly, separable. You can examine the representation without fundamentally altering it. In quantum systems, that separation becomes less clear, because a quantum state does not just represent information, it embodies it. The state of the system is the information. And as we've seen, that state cannot be fully observed without changing it. So the representation is not something you can hold at a distance. It's something you have to interact with, carefully, and that interaction is part of the process. Now, from a mainstream perspective, this is simply how quantum information works. The mathematics defines the state, the operations transform it, and measurement extracts information. But conceptually, it introduces a different relationship between observer and system. Because instead of observing a representation from the outside, you are participating in the process that defines it. And that subtle shift has implications. Not in a dramatic or immediate way, but in how we think about systems that are built on these principles. Because it suggests that information, at a fundamental level, may not be something that exists independently of interaction. It may be something that emerges through it. Now again, this idea doesn't require any departure from established physics. It can be understood entirely within the framework of quantum mechanics, but it does invite a slightly different perspective, one where representation is not static, but dynamic, not fixed, but evolving. And this becomes particularly interesting when you consider how quantum systems are initialized. Before a computation begins, qubits are prepared in a specific state. This preparation defines the starting point of the system's evolution. But because of superposition, that starting point can already contain multiple possibilities. So even the initial representation is not a single fixed value. It's a distribution, a structured set of potential outcomes. And from that starting point, the system evolves, transforming that distribution through a series of operations until measurement produces a result. Now, if you look at this process from a purely technical standpoint, it's well understood. But if you step back slightly, it begins to resemble something more general, a transformation of possibilities into outcomes, guided by rules, but not strictly determined in advance. And that pattern shows up in other areas as well, not necessarily in the same form, but in a similar structure, where systems begin in a range of possible states, evolve through interactions, and eventually settle into a particular configuration. Now, it's important not to overextend the analogy. Different systems have different rules, different constraints, but the structural similarity is worth noticing, because it suggests that quantum computing is not just a specialized tool, but part of a broader class of processes that involve the evolution of possibilities into actualities. And that brings us to another subtle point: the role of constraints. In classical computing, constraints are explicit. They are defined by the program, the logic, the structure of the algorithm. In quantum computing, constraints are still present, but they are often embedded in the way the system is set up. The initial state, the sequence of operations, the design of the algorithm, all of these shape the space of possibilities that the system can explore. So instead of directly specifying the solution, we define the conditions under which the solution is likely to emerge. And that approach has an interesting consequence. It shifts the focus from control to design, from telling the system exactly what to do, to creating a framework in which certain outcomes become more probable. And that's a different way of thinking, not just in computing, but in problem solving more generally, because it emphasizes the importance of structure, of setting up the right conditions, rather than trying to dictate every step. Now, this idea is already present in other areas: optimization, machine learning, even certain types of engineering. But quantum computing brings it into a more fundamental context, because the system itself operates on principles that naturally support this kind of approach, and as a result, it may influence how we think about designing systems in other domains, not as rigid sequences of instructions, but as environments where desired outcomes can emerge through interaction. And this connects back to something we've been circling around throughout this entire exploration: The idea that quantum computing is not just about doing the same things faster, but about doing certain things differently, in a way that reflects the underlying structure of the systems it's based on. Now, whether this leads to broader changes in how we approach computation remains to be seen. Classical methods are deeply established, highly effective, and not easily replaced. But in specific areas, particularly those involving complex, high-dimensional systems, this different approach may offer advantages, not just in performance, but in perspective. And that perspective is still evolving, still being refined. As researchers experiment with new algorithms, new architectures, new ways of controlling and measuring quantum systems, each step revealing a little more about how these representations behave and how they can be used, not in a way that fully resolves the deeper questions, but in a way that makes those questions more precise, more connected to actual systems, more grounded in observation. And that, in many ways, is how understanding progresses, not through sudden answers, but through gradual refinement, through patterns that become clearer over time, through ideas that shift slightly as new information comes in. And quantum computing, with all its complexity and subtlety, is very much part of that process, a process that is still unfolding, still open, still inviting careful attention, rather than quick conclusions. As we move closer to the outer edges of this exploration, there's one more layer that begins to settle into view, one that ties together many of the ideas we've been circling around, but does so in a quieter, more reflective way. It's the question of perspective, not just how quantum computers work or what they might achieve, but how engaging with them gradually reshapes the way we interpret reality itself. Because throughout this journey, a pattern has been forming, not in a dramatic or obvious way, but in small, consistent shifts. We started with bits and qubits, with clear distinctions between classical and quantum systems. But as we followed the details, superposition, entanglement, measurement, uncertainty, interaction, those distinctions began to blur, not disappear, but soften. And in their place, a more layered view began to emerge. One where systems are not strictly one thing or another, but exist along a spectrum. One where behavior depends on context, interaction, and scale. One where outcomes are not always predetermined, but shaped through processes that unfold over time. Now, this perspective doesn't replace the classical view, it sits alongside it. Classical models still work remarkably well for most of the world we interact with. They provide stability, predictability, and clarity, but quantum computing introduces a complementary viewpoint, one that becomes relevant when we look closer, when we examine systems at a level where classical assumptions begin to break down. And that dual perspective, classical and quantum, creates an interesting tension, because it means that there is no single, complete way of describing reality that applies equally at all scales. Instead, we have multiple frameworks, each effective within its own domain. And quantum computing operates at the intersection of those frameworks. It translates quantum behavior into something we can interact with, while still being constrained by the classical systems we use to control and measure it. And that intersection is where many of the most interesting questions arise. Not because it provides clear answers, but because it highlights the boundaries of our current understanding. And boundaries, as we've seen, are often where new ideas begin to take shape. Now, as these systems continue to develop, there's a natural tendency to focus on their practical impact, what they will change, how they will be used, which industries they will affect. And those are important questions. But there's also value in stepping back and considering the quieter influence they may have, the way they gradually shift how we think. Because engaging with quantum systems requires a different kind of intuition, one that is comfortable with probabilities instead of certainties, with relationships instead of isolated states, with processes that are not always directly observable, but still produce consistent results. And over time, that way of thinking can extend beyond the technology itself. It can influence how we approach complex problems, how we interpret uncertainty, how we understand systems that don't behave in simple, linear ways. Now, this doesn't mean that quantum mechanics becomes a universal lens for everything. Different domains require different models, but the exposure to these ideas, the repeated interaction with systems that behave in this way, can have a subtle effect. It expands the range of perspectives we can draw from, and that expansion is not always immediate or obvious. It happens gradually, through familiarity, through repeated observation, through the accumulation of small insights that begin to connect. And this is where quantum computing becomes more than just a technological development. It becomes part of a broader shift in how we engage with complexity, not by simplifying it away, but by finding ways to work within it, to navigate it, to extract useful patterns without needing to fully reduce them to simple rules. And that approach, while still evolving, may become increasingly relevant as systems in many fields grow more complex, not just in physics or computing, but in areas like biology, economics, and even social systems. Because complexity, at its core, involves interactions between many components, often with outcomes that are not easily predictable from the individual parts. And quantum systems, by their nature, operate in that kind of space. They don't just handle complexity, they embody it. Now again, it's important to stay grounded. The principles of quantum mechanics apply specifically to certain types of systems, under certain conditions. They are not a universal explanation for all complexity, but they do provide a working example of how such systems can be understood, at least in part, through probabilities, through interactions, through structured uncertainty. And as we continue to build and refine quantum technologies, we are, in a sense, learning how to think in those terms more naturally, not abandoning classical reasoning, but complementing it, adding another layer to how we interpret the world. And that layered perspective may be one of the most lasting effects of this entire field. Not just the machines we build, but the mindset they encourage. A mindset that is comfortable operating at the edge of certainty, that recognizes the limits of observation without seeing them as barriers, that values patterns and consistency, even when full transparency is not available. And perhaps most importantly, a mindset that remains open. Because as we've seen throughout this exploration, quantum computing does not present a closed, complete picture. It presents an evolving one, a system of ideas that continues to develop as new experiments are conducted, new technologies are built, and new questions are asked. And those questions are not signs of failure. They are signs of progress, indicators that we are moving into areas where understanding is still forming, where the answers are not fixed, but emerging. And in that space, there is room for careful thought, for curiosity, for exploration that doesn't rush toward conclusions, but takes the time to examine each layer as it appears. Because sometimes, the most valuable insight is not the answer itself, but the way the question changes as we learn more. As we approach the final stretch of this exploration, there's a quiet realization that begins to settle in, not as a conclusion, but as a kind of perspective that ties everything together. It's the idea that quantum computing, for all its complexity and potential, may ultimately be less about the machines themselves, and more about the relationship it reveals between us and the systems we try to understand. Because throughout this entire journey, a pattern has repeated itself in different forms. We begin with something that appears clear, bits and logic, inputs and outputs, predictable systems that behave in ways we can trace and explain. Then we look closer, and the clarity starts to shift. Not disappear, but expand into something more nuanced. Probabilities replace certainties. Interactions replace isolated steps. Observation becomes part of the process, rather than something separate from it. And with each step deeper, the boundary between what we observe and how we observe it becomes a little less defined. Now, from a scientific standpoint, this is not a new idea. Quantum mechanics has always implied that the observer plays a role in the system, at least in terms of measurement. But quantum computing brings that implication into a more practical context. Because we are not just observing these systems, we are building them, using them, depending on them to produce results. And that practical engagement makes the relationship more immediate, more tangible. It's no longer just a theoretical consideration. It's something that affects how the system operates, how the results are obtained, how the entire process unfolds. And this leads to a subtle shift in how we think about control. In classical systems, control is direct. You define the steps, the system follows them, and the outcome is determined by that sequence. In quantum systems, control is more indirect. You prepare the initial state, design the transformations, and then allow the system to evolve according to its own rules. You guide the process, but you don't dictate every detail. And that distinction is important, because it reflects a broader principle that appears in many complex systems. The idea that control is often about shaping conditions, rather than specifying outcomes. And quantum computing makes that principle explicit. Not as a philosophical concept, but as a practical necessity. You cannot force a quantum system into a specific outcome without losing the very properties that make it useful. You have to work with the system's natural behavior, align with it, design around it. And that requires a different kind of thinking, a different kind of interaction. Now, this doesn't mean that we lose precision or reliability. Quantum algorithms are carefully constructed, rigorously tested, and capable of producing highly accurate results. But the path to those results is not always something we can fully control or observe in the traditional sense. And that brings us back to something we've touched on several times, but that becomes clearer here. The idea that understanding, in this context, is not about complete visibility. It's about consistency, about patterns that hold true across repeated observations, about systems that behave in reliable ways, even if the internal details are not fully transparent. And that kind of understanding is not unfamiliar. It appears in many areas where complexity is high and direct observation is limited. But in quantum computing, it is built into the foundation. And that makes it more visible, more central to how the system operates. Now, as these technologies continue to develop, there will likely be advances that improve transparency, that provide better tools for analysis, that deepen our understanding of how these systems behave internally. But it's also possible that certain aspects will remain inherently difficult to observe, not because of a lack of effort, but because of the nature of the systems themselves. And if that's the case, then the way we relate to these systems may continue to evolve, not toward complete control and full visibility, but toward a balance between what can be directed and what must be allowed to unfold, between what can be known in detail and what can be understood through patterns and outcomes. And that balance is not something that can be defined once and for all. It shifts. It adapts. As the systems become more advanced, more integrated, more connected to the broader world. Because eventually, quantum computing will not remain confined to specialized environments. It will interact with classical systems, with networks, with real-world applications. And in that interaction, the distinctions we've been exploring between quantum and classical between observation and process, between control and emergence, will become part of a larger, more integrated framework. A framework that reflects both perspectives, not as competing views, but as complementary ones, each relevant in its own domain, each contributing to a more complete picture. And that picture, even as it becomes clearer, is unlikely to ever feel entirely finished. Because the deeper we look, the more we encounter layers that invite further exploration. Not in a way that suggests something hidden or unreachable, but in a way that reflects the natural complexity of the systems we are engaging with. Systems that are not static, but evolving. Not isolated, but interconnected. Not fully transparent, but consistently structured. And within that structure, there is still a great deal to learn. Not just about how quantum computers work, but about what they reveal, about the nature of information, the behavior of systems, the relationship between observation and outcome, and perhaps most quietly of all, about the limits and possibilities of understanding itself. Because in the end, what this field offers is not just a set of tools or technologies. It offers a way of engaging with questions that don't have simple answers. Questions that require patience, careful thought, a willingness to stay with uncertainty without rushing to resolve it. And that kind of engagement tends to lead somewhere interesting, not always predictable, not always immediate, but steadily, consistently, forward. And now, as everything begins to settle into place, what remains is not a single conclusion, but a quiet sense of perspective that has been building, layer by layer, throughout this entire exploration. Because if you trace the path we've taken, from the basic idea of qubits, through superposition and entanglement, into questions of information, time, networks, limits, and interpretation, you begin to notice something subtle. At no point did the mystery disappear. It changed. It became more refined, more structured, more grounded in real systems and real observations. But it never fully resolved into something simple or complete. And that, in itself, may be one of the most important things to understand about quantum computing. Not that it hides answers, but that it reveals how answers can exist without closing the question. Because from a purely practical standpoint, the progress is undeniable. Quantum computers are no longer theoretical constructs. They exist, they function, and they are steadily improving. Researchers are extending coherence times, increasing qubit counts, refining error correction, and developing algorithms that demonstrate clear advantages in specific domains. All of that is real. All of that is measurable. And yet, alongside that progress, the deeper questions remain. What is a quantum state beyond its mathematical description? What does it mean for possibilities to exist simultaneously? What determines the outcome of a measurement? Are these processes purely abstract, or do they correspond to something physically real at a deeper level? And perhaps most quietly of all, is there a point where explanation reaches its natural limit? Now, from a mainstream perspective, these questions are approached with caution. The focus remains on what can be tested, what can be predicted, what can be verified through experiment. And that approach has been extraordinarily successful. It has given us technologies, insights, and tools that would have seemed impossible not long ago. But the existence of those tools does not eliminate the questions that surround them. If anything, it sharpens them. Because the more precisely a system behaves, the more clearly we can see the boundaries of our understanding. And quantum computing, in its current form, sits right at that boundary. Not beyond it, not outside of it, but directly on it. Operating within a framework that works perfectly in practice, while still inviting deeper interpretation. And that dual nature, precision without complete explanation, is what gives this field its unique character. It's not just a frontier of technology, it's a frontier of perspective, a place where established knowledge and open questions coexist, not in conflict, but in balance. And as we've seen, that balance shows up in many different ways. In the relationship between classical and quantum systems, in the interplay between observation and outcome, in the distinction between simulation and replication, in the limits of computation and the possibilities that remain. Each of these areas reflects the same underlying pattern: a system that is consistent, structured, and reliable, but not fully transparent. And that pattern may extend beyond quantum computing itself, because it suggests something more general about how complex systems behave, that they can be understood in terms of patterns and relationships, even when their internal processes are not completely accessible, that they can be used effectively, even when their full nature is still being explored. And that understanding, in these cases, is not about eliminating uncertainty, but about working within it. Now, none of this requires stepping outside the bounds of science. The principles we've discussed are grounded in established theory, supported by experimental evidence, and actively being developed by researchers around the world. But staying grounded does not mean avoiding the deeper questions. It means approaching them carefully, without overreaching, without assuming conclusions that haven't been demonstrated, and at the same time, without ignoring the patterns that continue to appear, because those patterns are what guide the exploration forward, not all at once, not in dramatic leaps, but gradually, through observation, experimentation, and reflection. And that process is still ongoing. Quantum computing is still in its early stages. The systems we have today are limited, specialized, and far from their full potential. But they are enough to show that the principles work, and that there is more to explore, much more. And as that exploration continues, it will likely bring new insights, new technologies, and new questions. Questions that build on what we've discussed here, but extend into areas we can't fully anticipate yet. Because that's how fields like this tend to develop. Not in a straight line, but in a series of expanding circles, each one revealing a little more of the structure, while also pointing outward to what remains unknown. And within that process, there is something quietly consistent, a kind of rhythm, where understanding grows, not by replacing uncertainty, but by organizing it, giving it shape, context, meaning, without ever fully removing it. And perhaps that's the most fitting way to leave this topic, not with a final answer, but with a clearer view of the landscape. A landscape where quantum computers are not just tools, but indicators. Indicators of how reality behaves at its most fundamental level. Indicators of how information can exist, evolve, and resolve. Indicators of how much we can know, and where that knowledge naturally begins to fade into deeper questions. And in that space, between what is known and what is still unfolding, there is room for curiosity, for careful thought, for exploration that doesn't rush, but moves steadily, one idea at a time. Because sometimes, the most meaningful progress is not in reaching a conclusion, but in learning how to follow the question a little further than before. And for now, that's where we'll leave it. Not at an ending, but at a point of quiet continuation, where the ideas remain open, and the exploration goes on.